Good, good evening, students. Today we have to discuss about heat capacity. Today we have to discuss about heat capacity. In the last video, we discussed the enthalpy, significance of enthalpy, and that of the first law of thermodynamics. So today we have to discuss about the heat capacity. Heat capacity means the amount of heat required. Heat capacity means the amount of heat required, the amount of heat required to increase the amount of heat required to increase the whole mass of the system, the whole mass of the system, whole mass of the system through 1 degree centigrade. Through 1 degree centigrade. This is called heat capacity. So the amount of heat required to increase the whole mass of the system through 1 degree centigrade. What is the amount of heat required? That is called heat capacity. What is the mathematical expression? Mathematical expression is that it is defined as the quantity of heat required, quantity or amount, quantity of heat required to increase the whole system, system means which contains some substance, whole system from temperature at T1 to the high temperature T2, from the low temperature T1 to the high temperature T2. That is called heat capacity. That means my formula is C is equal to Q. Q means quantity or amount of heat required. Temperature, low temperature to high temperature, T1 to T2. Always we subtract final minus initial. Final temperature is T2. T2 minus T1. That means Q by delta T. If we take very small change in heat, so C is equal to dQ by dt. C is equal to dQ. You remember here that we know that Q, heat and temperature are path functions. So here we cannot write delta. We can write here C is equal to del Q by dt. Where del Q means del Q is the small quantity of heat. Del Q is the small amount of heat supplied to the system. So the temperature changes. The temperature change is dt, small change temperature. You have to supply small heat, so small temperature is change. That is called the heat capacity. But remember, heat capacity means you have to take any amount of the substance. If you take 10 gram of water, heat capacity suppose is 30 joule. Suppose 10 gram water you take, heat capacity is suppose 30 joule. If you take 100 gram water, then heat capacity should be 300 joule. So if the amount of the substance change, heat capacity also changes. This makes a problem, because if anyone tells that heat capacity of water is 30 joule, then it is without mentioning the amount, then it is completely useless. You have nothing to use, because heat capacity changes with the change of the amount of the substance. So that is why it is very less used. That means heat capacity is very less used. So in that cases what happens, and from the heat capacity also we know that in gaseous system, the system is gaseous state. In gaseous system, heat capacity at constant pressure, at constant pressure, heat capacity at constant pressure is different. In gaseous system, heat capacity at constant pressure is different to that of constant volume. That means, suppose the system is in the gaseous state, heat capacity at constant pressure has different value, and heat capacity at constant volume has different value. There are two different value you can get. One is heat capacity at constant volume, something different value, and heat capacity at constant pressure is something different value. So that happen in case of gaseous system. Suppose I tell that heat capacity at constant volume. Suppose we take, according to the first law of thermodynamics, del Q is equal to du plus pdv, is according to the first law of thermodynamics. Suppose I tell that at constant volume, at constant volume means dv is equal to 0. That means dv is equal to 0 means pdv, this is equal to 0. So your del q is equal to du. So my heat capacity, and at constant volume, heat capacity can be mentioned as cv. C is equal to cv. At constant volume, heat capacity C is equal to Cv. At constant volume, dV is equal to 0. So pdv is equal to 0. So del K is equal to del U. So my heat capacity formula, that we know that C is equal to del Q by dt. So it can be written as C, in place of C I write Cv, and in place of del Q I write du, and remain is same as dt but at constant volume. This is the heat capacity at constant volume in case of gaseous system. Similarly, we know that enthalpy formula is dH is equal to du plus pdv. At constant pressure, at constant pressure, dH is equal to dq. dH is equal to del q at constant pressure. So what happens at constant pressure, dH is equal to del q. So in place of we know that C is equal to del q by del T. This is the heat capacity that we know. But at constant pressure, dH is equal to del q and C is equal to Cp. So in this case, we write, in place of C I write Cp, in place of del q, because at constant pressure dH is equal to del q, and dH formula is dH is equal to du plus pdv. Del q also du plus pdv. At constant pressure both dH is equal to del q. So in place of del q I write dH by dt at constant pressure. This is called heat capacity at constant pressure. So if that means if we consider 1 mole of the substance, remember here we do not mention any amount. If the amount change, heat capacity will change. But suppose you take 1 mole of the substance. For 1 mole substance, for 1 mole, for 1 mole of substance, then Cp is called molar heat capacity. Molar heat capacity. Okay, for 1 mole of the substance, if you take 1 mole of the substance, Cp is called molar heat capacity. Similarly, for 1 mole of substance, for 1 mole of substance, Cv is called molar heat capacity. Molar heat capacity at constant volume. At constant volume. Similarly, for 1 mole of substance, Cp is called molar heat capacity at constant pressure. It is at constant pressure. Okay, that means we can define in gaseous system heat capacity at constant pressure is different to that of the constant volume. Here you see that value is different. So del Q is equal to du plus P dV. At constant volume dV is equal to 0. So del Q is equal to du. So C is equal to del Q by dt. That means in place of del Q I can write du, because del Q is equal to du at constant volume. So see, this is called heat capacity at constant volume, and we know that dH is equal to du plus P dV, and del Q also we know that du plus P dV. So both right hand side is same. So du plus P dV, here du plus P dV, here also du plus P dV. But dH is at constant pressure. When we say enthalpy means it is constant pressure. When we say internal energy means constant volume. So both right hand side is same. So dH is equal to del Q. So dH is equal to del Q. So in place of del Q I can write dH. So dH is equal to dt, constant pressure. So for if you take 1 mole of this substance, then this Cp is called molar heat capacity at constant pressure. If you take 1 mole of this substance, this Cv is called molar heat capacity at constant volume. This is all about the heat capacity. But heat capacity, we cannot, no one use the heat capacity, because when this amount of the substance change, heat capacity also changes. This makes many difficulties. That is why the another term we get, that is called specific heat capacity. That is called specific heat capacity. Specific heat capacity. Just day before or 1-2 days back or 1 day back, Malaya somewhere something about specific energy they told about. Specific energy, but that is popularly known as, generally we in research purpose we use, that is called the energy density. Instead of specific energy, no one use specific energy, because specific energy is, though we in books it is written, but in research purpose and modern use we called it as energy density. Energy density means the amount of the quantity of energy required per unit volume. Remember, per unit volume of the substance. That is called energy density. Instead of specific energy, you call energy density, because in modern purpose we all use energy density instead of specific energy. Specific energy written in the books somewhere, I also search it, but it is generally written. But when you use it for modern purpose, that means nowadays for research purpose we call it as energy density. So instead of specific energy, you call it as energy density. So here the specific heat capacity, it is very important because here specific heat capacity, the amount of the substance is fixed. Amount of the substance does not change, but amount of the substance is fixed. In specific heat capacity means the amount of heat required, the amount of heat required to increase the temperature, to increase the temperature of unit mass. Unit mass means 1 gram. Unit mass, to the temperature of unit mass of substance through 1 degree centigrade. Through 1 degree centigrade. In case of heat capacity, what you know? Whole mass of the substance. In place of unity mass, you take whole mass. In case of heat capacity, that is why heat capacity is useless. But we all use specific heat capacity because it takes unity mass. Unity mass of the substance through 1 degree centigrade. That means if you measure, you synthesize or you prepare a substance or you prepare a new alloy or you prepare something new compound, if you want to find out what is its heat capacity, that means you have to convert it into specific heat capacity, because throughout the world it will remain same. The value will be remain same. If in India whatever you calculate, in USA go, it will be the same value. But in case of heat capacity, as if I take in 10 gram, if it has some different value of heat capacity. If USA, someone take 100 gram, amount different heat capacity will different. So in specific heat capacity is more important than that of the heat capacity. So you always use the specific heat capacity, because in this case we take unity mass instead of whole mass. We take the unity mass of the substance, and all other things remain same, because Q means, suppose we know that heat capacity C is equal to, we tell that Q by dt. That we, from the previous we know that. Then Q is equal to C dt. C is called heat capacity. Okay, here C is heat capacity. In this case, what is called? C is called heat capacity. So heat capacity means here amount of the substance is present. So then we can write that Q is equal to mass of the substance into specific heat capacity into dt. dt means final temperature minus initial temperature. This whole thing is nothing but C. C means heat capacity. Specific heat means 1 gram. Suppose I tell that 1 gram substance has heat capacity 10 joule. That is called specific heat capacity. Suppose you take 10 gram. 10 gram will carry 100 joule. 10 into 100, 10 into 10 is equal to 100 joule. So here mass is 10 gram, specific heat for 1 gram. Then heat capacity split into mass into specific heat capacity, T2 minus T1. So if at constant pressure we consider, at constant pressure you consider, then your Q is equal to mass of the substance. If I write in Cp, same symbol, and here you write T2 minus T1, where khali naming is changed. Cp is called specific heat capacity. Specific heat capacity at constant pressure. So this is the quantity of heat required. This is the quantity of heat required. This Q value means Q is the quantity of heat required. Q is the quantity of heat required. Quantity of heat required to increase the mass of the substance from from T1 to T2, low temperature to high temperature. Similarly, at constant volume, Q is equal to same M into CV into T2 minus T1, low temperature to high temperature, where CV is called specific heat capacity at constant volume. This is called specific heat capacity at constant pressure, specific heat capacity at constant volume. This Q is called quantity of heat required, amount of heat required. But how I already derived Cp value, Cv value. In another way also you can derive. In another way you can also derive the value of Cp and Cv. How you derive? Suppose according to the first law of thermodynamics, del Q is equal to du plus P dV. We know that suppose at constant volume I consider Cv is equal to du by dt, constant volume, that we know Cv, or you can call it as, or we have to derive this one. Okay, so del Q is equal to du plus P dV. We know that C is equal to del Q by dt. That we know from the heat capacity value. Then C dt is equal to del Q. So in place of del Q I write this thing. That means C dt is equal to du plus P dV. So at constant volume, suppose I consider this is called C dt, du plus P dV. Suppose at constant volume, at constant volume dV is equal to 0 and C is equal to Cv. So in here we write Cv dt by Cv is equal to du plus P dV by dt. I take this dt to the denominator. At constant volume dV is equal to 0. So this will be 0. 0 into something 0. Then what we get? Now Cv is equal to du by dt at constant volume. In this way also you can derive. Similar also you can derive from this at constant pressure. Suppose at constant pressure, constant pressure C is equal to Cp. Then in place of Cp I write that Cp dt is equal to du plus P dV. So your Cp is equal to du plus P dV by dt. Okay, that we get from, suppose it is equation 1. We know that dH is equal to enthalpy, du plus P dV. So differentiate this equation, differentiate with dt. dt differentiate, so we get dH by dt, then du by dt plus P dV by dt. Now you compare this thing, you just expand it, we get du by dt plus P dV by dt. You see here, right hand side both are same. This one is equal to this one, so this one is equal to this one. So Cp is equal to dH by dt in y and constant pressure. In this way also you can find out Cp and Cv. Next is derivation. Cp minus Cv is equal to R. Cp minus Cv is equal to R. How we derive the Cp minus Cv? Derivation of Cp minus Cv is equal to R. How you derive the Cp minus Cv is equal to R? In that case, what you know? Now from first law of thermodynamics, we know del Q is equal to du plus Pdv. For ideal gas equation, ideal gas equation is equal to PV is equal to nRT. PV is equal to nRT. For 1 mole of gas, n is equal to 1. So equation becomes PV is equal to RT. Now you differentiate means PdV is equal to RdT. So in place of PdV, I write this RdT. So my equation becomes del Q is equal to du plus RdT. Okay, we know that Cv is equal to du by dt at constant volume. Then Cv dt is equal to du. Take dt to this side, du. So in this du I can write Cv dt. So my del Q is equal to Cv dt plus R dt. At constant pressure, dq del Q is equal to dH. Both right hand side is same because del Q is equal to du plus Pdv. dH also du plus Pdv. Both right hand side is same. So left hand side is equal to del Q is equal to del H. So instead of del Q I write dH. dH is equal to Cv dt plus R dt. We know that Cp is equal to dH by dt at constant pressure. So Cp dt is equal to dH. So instead of dH I write Cp dt. Cp dt is equal to Cv dt plus R dt. Now take dt, all cases cancel. We get what? Cp is equal to Cv plus R. Take Cv to this side. Cp minus Cv is equal to R. Okay, this is the proof. Cp minus Cv is equal to R. Cp minus Cv is equal to R. So time okay, also 5 minutes. So in that case what happens? Now for reversible process at constant volume, for reversible process of constant volume, what we get? Now we get is equal to Q is equal to M into Cv into dt. This is for reversible process, and Cv is equal specific heat capacity. Specific heat capacity at constant volume. Similarly, for reversible process at constant pressure, process of constant pressure at constant pressure Q is equal to m into Cp into dt, where Cp is called specific heat capacity, specific heat capacity at constant pressure, specific heat capacity at constant pressure. This is equal to Cp and Cv, but condition is that the value of Cp and Cv is same for ideal gas, at all temperature and pressure, at all temperature and pressure, but value of Cp and Cv is different for real gas, at all temperature and pressure, at all temperature and pressure. Okay. सड़ा मूषा गुड़ाक हे ना ऑटोमेटिक कर देछि कलम उठेले बंद हो मूषा ए टाइम भी गलानी how start कर the constant pressure. Next class the derivation is there, we derive the work done. Okay, खुदा हाफिज.